Now for this symmetric trajectory of projectile motion, we managed to find the equation of trajectory as a parabola of this one. As you can see, as I said before, at each instant of time in this path of motion for a projectile, you have an x and y position, and you can find for each x a corresponding y as well. By substituting here x, and then you're going to get y if theta naught and v naught are given in the problem. So it's interesting to see here for a certain theta naught or a certain angle, you might have such path like this. If you just insert different values of x in here, you're going to get the corresponding points or the corresponding values of y, and then you draw this path motion. If you change, obviously, as you can see, you can change the angle, and you can get also a parabolic path with different shape, with different shape, about a different parabola. So again, we have to come back here to make this notice that you have this trajectory with a symmetry around this dashed line, where the left hand side of the motion you have the component of velocity is decreasing while it's going up because of the pull of the gravity downwards. So that's why the velocity component along the y-axis is decreasing until it reaches a turning point where the component of velocity here is zero, and then the projectile comes back again downward under the pull of the acceleration of gravity. As you can see, from Vy equals 0, the component of velocity start increasing until it reaches a value of Vy here at the point where the trajectory intersects the x-axis. And the value of the velocity in here, this one, is equals to minus v naught y. As I said before in the previous sessions, the magnitude of the velocity vector and the final destination is the same as the magnitude of the velocity vector along the y-axis at the initial starting point with a different sign. Of course, it is clear here at each single point along the trajectory, you're going to get any point on this side, you have a corresponding point on the other side. If you draw a line along parallel to the x-axis, you're going to get the magnitude of the velocity on the left side is the same as the magnitude of the velocity on the right side along the y-axis. And again, the angle that the velocity makes at each instant of time with the horizontal is going to be positive all the way up to the end here, and then this angle starts to become below the horizontal, as you can see at each single point here and there in the trajectory. Also, you can find the magnitude of velocity here from the component of x-axis and y-axis, the magnitude and the direction as well. And you have to make, you can check what we said, that the angle, if the angle here, for example, 30, you might get it up here at the end minus 30, as we said before. Having this symmetry in the trajectory, we're going to derive two expressions just for the symmetrical path trajectory, one for the horizontal range and the other one for the maximum height. To do that, let's start with the horizontal motion, where we have Vx equal V naught x, while in the y motion we have Vy equal V naught y minus gt. However, delta x in the horizontal motion equal V naught x by t, while delta y equal V naught y, but the product of V naught y by t minus half gt square. In order to get the projectile, we have to set again the initial conditions as we did before, where we have V naught x equal V naught V naught x equal V naught cosine theta, while V naught y equal V naught sine theta. Then we can use the equation for delta y, where delta y here for the whole trip from this point to this point, obviously delta y is going to be 0. If you put delta y equals 0 in this equation, you're going to get here 0 equal V naught y minus half gt squared. This allows us to find the time of a flight for the whole trip of the projectile, and that is equal to 2 V naught y divided by acceleration due to gravity, and this is nothing more than 2 V naught sine theta naught by g. Using the x, or the horizontal motion, the x on the delta x equal V naught x times t, where x naught equals 0 as we said before, then we are able to find for delta x, for the whole range here, for delta x, we call it r, equal the product of V naught x, as I said, by t. Having t from previous equation from the y-axis, and then put it in there, we're going to get an answer for the range V naught squared sine 2 theta naught divided by g. To find an expression for the height, simply use the same equation as before, delta y equal V naught y, t at the maximum height. So we're going to use just this part of the equation from here up to here, half of the projectile. And the time at the upper half here, th, until it reaches here from the start, we're going to get it from this equation. So delta y is positive, which is equal to h, and h is going upward. That's why we got that. And then V naught sine theta, we substitute V naught sine theta instead of V naught y, and then solve this equation. You're going to get h equal V naught squared sine squared theta naught divided by 2g, and this is an equation for the height. Again, we have to remind you that these two equations just derived now, this one and this one, are applicable just for the symmetrical trajectory. This is just for this one, and then you can use it in other trajectories. And also we have to put some emphasis on this point, as we said before. Vy at the end here is can be justified and can be proved to be equal to minus V naught y by using this equation and substituting the value of t from here for the whole trip, and then we're going to get V naught y in here.
At what angle should a ball be launched in order to fly the greatest distance before striking the ground? This spring-loaded gun can launch small wooden balls at different angles with the same speed. As we shoot each ball, we will track its position with a line on the screen, using a different color for each angle of firing.
Using the obtained relation for the range, we can show that with different initial angles, we can get different trajectories, as obviously shown in the figure, by shooting the projectile with this initial velocity. Now, what is important in here, if we keep the same initial velocity and each time, and then we'll get the range, this range, as for instance 125, with this initial velocity, we can get two values for theta. Not only this 15 degrees, we can find a complementary angle of 75 that goes the same range but with different angles when we keep the initial velocity is the same. Again, for the same initial velocity, you might have two complementary angles that the projectile can reach the same range in them. So these two angles, 15 and 75, as you can see, you can reach the same range of the projectile with the same initial velocity. These are called complementary angles. Obviously, in this case, the heights are different from this one and this one. Also, from this relation, we can get the maximum range. As we know, sine theta is equal to 1. This is the maximum value for the sine to take. When you put that, the angle that makes sine theta equal to 1 is obviously 90. So we have to have 2 theta naught equal 90 degrees. This means that theta naught with 45 degrees gives us the maximum range. So when theta equal 45, the range becomes maximum range. We can call it maximum range.